Hello, welcome to Teach You Why. I hope everyone here has done well for your practical exams. And even if think you have not done well enough, it is okay. Most importantly is that you move on from here and focus on the remaining papers. There will be still chance for you to improve your grades moving on now. So today walkthrough will be on Zhong Hua 2020 paper, which is also another challenging paper in my opinion. And as usual, the link to the paper will be as shown in the description below, where you can download and practice them on your own before watching this video. And without further ado, let's get started with the walkthrough. Okay, on the first question, so first question shows three charge, Q1, Q2, Q3. Alright, so the information of the charge is shown in the question. Q1 and Q2 are positively charged. So let me label here, and likewise you should do so in your exam. Q1 and Q2 is positively charged and Q3 is negatively charged. Okay, so before we go on further, let's understand how are the charges interacting with each other. So we need to understand that Q1 and Q2 will repel each other, which means to say Q1, if let's say you are Q1, okay, you will experience a force this way, okay, due to Q2. It's like Q2 is like Q2, alright, trying to push away Q1. And then Q1 will be attracted to Q3 because positive and negative charges attracts. So we have a attracting force in this manner. Okay, so how do we draw on this? How do we sketch first? So first it looks like this. So both of them will have equal and opposite force repelling each other. All right, and then we have a attractive force. Okay, this way in, this way in. All right, so okay. So let's see. Q2 acts on Q1 with a force of 5 newtons. So Q2 acts on, so this is over here, this is 5 newtons. So this is 5 newtons. And then Q1, and then Q3 acts on Q1 with a force of 3 newtons. So over here, this is 3 newtons. Okay. And then this is called FB, this is called FA. So essentially we have already the free body diagram of Q1, okay, which is what we want to draw. And then you see, determine the resultant force of FA and FB acting on the charge Q1 by means of scale diagram. Okay, so first of all, before I always start with any vector diagram, I draw the free body diagram to better understand how we can draw I will draw the free body diagram to better understand how I can go about to draw the vector diagram. So I will try as much as possible to use my ruler, my virtual ruler, but in the exam it will be way easier. So you can set any scale. Typically we like a round number, so let's set 1 cm to 1 newton. Okay, and then let's start with a point. Let's start with a point here. Okay, and then we need to draw to scale. So let me start with the easy one first. Let me start drawing FA. Okay, FA. So FA is this way. Oh. Okay, bear in mind I need to be in scale, to scale. So let me adjust. So this is 1 cm, 2 cm, 3 cm, 4 cm, and 5 cm is here. Okay, so you will do better on, it is easier for you to draw using an actual ruler. For me, I'm using a virtual ruler. Now, so this is FA. Okay, let's draw that direction here. And then now I'm going to draw FB. FB. FB is pointing outwards. Okay, so same thing. Okay, take note, why am I using 37 degrees against the horizontal? Because if you take note here, FB is 37 degree from the horizontal, and therefore let me now draw FB. FB will be how many cm? 3 cm, because it's 3 newtons. So this is 1, 2, and 3. So it's around here. Okay, so let me draw this. Alright, and there we have it. Now, so in this case, how should we we have already completed the vector diagram. All we need to do is just to complete the triangle. So I will use another color ink to complete the triangle. Alright, and then there we have it. Now this is where a lot of students have problems. What kind of problems? They'll ask whether am I going to draw the arrow this way, or whether am I going to draw the arrow this way. Now, in my previous videos, if you go ahead and check it out, I have already mentioned when we will use the arrow in this manner, or the arrow this. Now, what's the difference? If you take note, I'll repeat again. If you take note, this is what I call a zero resultant force. Okay, there is no resultant force. How come? So imagine you are a student. Okay, you run around the vector diagram. Can you see? You can follow around the vector diagram. It's completing one loop. So whenever the vector diagram is showing in this kind of orientation, this means that this is a zero resultant force. Okay, so let me write at a side and then show you to show you guys what it actually means. Okay, so if you have this kind, like go around the circle, this is no net force. Okay, now how about in this case here? In this case, there will be resultant force. Okay, so there will be resultant force. So this is FB. Okay, so there will be resultant force. And how I know that there is resultant force? So again, I use the student running around the track analogy. So if I have a student here, alright, so when you run around the vector diagram along the direction or along the arrow that is stated, right, you will see that as you run from FA to FB, okay, you notice that as you run along FA to FB, you will actually encounter like an opposite direction. And this kind of vector diagram is actually for a resultant force. Okay, and how do I know that there is a resultant force? Because firstly, the question typically will say, and in this case, the question did say that this is the resultant force of FA with FB. Alright, so hence we have this scale diagram. And what you can do is, so we need to find this this force resultant, FR. And then what I need to do is I use a ruler, I measure the distance, the length. So I don't have a proper ruler, so if you guys have a proper ruler, you should be able to measure it accurately. So on my ruler, it shows about 3.2 cm, which is approximately 3.2 newtons. Okay, so this is my resultant force, and then you need to measure the angle. So what is the angle? The angle will be, this angle will be about 35 degrees from the horizontal. So there we have it. We have this answer. So the resultant force will be stated as F resultant is equal to 3.2 newtons. Okay, and then you need to state the direction 35 degrees from the horizontal. Okay, so like I said, this is net force. Okay, moving on to the next question. Question 2. At a glance, you know that, or you can even guess that this topic is on light and refraction. So you have ray 1, 2, 3, 4 emerging from lamp 1.2 below the swimming pool. Critical angle of the water is 49 degrees. Okay, so part A. Complete the subsequent path for 4 rays in figure 2.1. Okay, so let's see how we can do it. I will use my ruler. So ray number 1, pretty straightforward. No incident ray. Okay, because this dotted line here is my normal. So there is no angle of incidence, no angle of refraction. So this light ray will just travel straight. Alright, no problem. This is easy. Now, how about ray number 2? Ray number 2, okay, ray number 2, there will be refraction. So this is water to air. So it's from dense to less dense. So what will happen from dense to less dense? We say that from less to less dense, the light will refract away from the normal. Now, what it means by away from the normal? So, I always get this kind of question, and how do we tell that it's away from the normal? So first of all, we draw a line that is supposedly this purple line, right, is supposedly how the light ray is supposed to travel without consideration of refraction. If there is no refraction, the light ray will just come out straight as if it is like a purple line. Okay, now because right now this is traveling from water to air, which means it's traveling out from a dense medium to less dense medium, we say that the light will travel and refract away from normal. So you see this light ray, right? Where's my normal? My normal is this dotted line here. So what I'm gonna do is, you see how my ruler turns. My ruler will turn away from the normal. Okay, so then this is my answer. So I will draw in red my answer. Okay, you will see my refraction away from normal. Alright, so this is my answer. Let me erase the purple one so as not to confuse you guys. Alright, for ray number 3, okay, ray number 3, we need to understand our definition of critical angle. What is critical angle? Critical angle means what? Critical angle means the angle of incidence. Okay, the angle of incidence such that it produces a refracted ray of 90 degree. Okay, that means the angle of refraction will be 90 degree. So in this case, let me draw this. So very clear cut, our answer is like this. So our angle of refraction will be this. Okay, this is ray number 4. Alright, so how about ray number 3 is like this. Okay, you have a right angle towards the surface. Ray number 4. Now we need to check. In this case, our angle of incidence is greater than our critical angle. So what will happen is that when this happens, okay, we will have what we call the total internal reflection. Alright, so let me just draw it this way. Alright, and then label this is also 60 degree. Alright, so there we have it. We have all these 6 marks. Okay, so calculate the refractive index and hence the angle of refraction for R2. Okay, so how are we going to calculate? So first of all, we understand that sine C, critical angle, is equals to 1 over n. N is your refractive index. Now we already know the critical angle, which is sine 45, okay, is equals to 1 over n. And hence, using your trigonometry, you will be able to solve for n. So n is equals to 1 over sine 45. Okay? No, hold on. Sine 45. So let me find my calculator. One divided by sine 45. Okay, so n is equals to 1.414. Okay, so 1.41, round off to 3 sig fig. Okay, so 3 sig fig is 1.41 3 SF. Okay, so how do we calculate the angle of refraction? So most students always make a mistake. They do trigger. They will be trigger happy. They put sine I over sine R equals to n. Now this is wrong. Why is that so? Because why in this case this is wrong? Why we cannot use sine I over sine R? Is because sine I over sine R is only used when it's from less than to more than. Okay, it's only used when it's less than to more than. So what happens when we have more than to less than? When the light ray is traveling from more than to less than, we need to swap it around. It becomes sine R over sine I equals to n. Alright, so this is a common mistake. So I please take note, don't do this, especially when you are traveling from more than to less than. This is for sine I over sine R is from less than to more than. If the question is showing you from more than to less than, please use sine R over sine I, or in other words, reciprocate your sine I over sine R. Okay, so sine R over sine I will be equals to 1.4. So sine R over sine I is 20 equals to 1.414. So we can find sine R. Sine R equals to times sine 20 okay, so sine R equals 0.4836. R is equals to, so you just need to do your simple trigonometry. Hold on. Okay, sorry, there was some technical glitch. So sine inverse 0.4834. Okay, R is 28.9 degrees. Alright, so refractive angle of refraction is 28.9. So this angle here is 28.9. Okay. Alright. So let's move on. Figures 2.2 shows how the light rays from the lamp forms a semicircle when viewed from the top of the pool. Okay, calculate the distance AB. Alright, so what it means is that, okay, let me erase this because I need to explain. So what it means is that, let's say you put your eyes here. Okay, you look on top. Okay, you look on top. So if you look on top, right, you will actually see a light ray from a bird's eye view like this. Okay, so this is me looking on top. Now, where do you think A is? A is definitely the light source. Okay. Now, what do you think B is? Common mistake. I would say common mistake. In this case, it's very tempting to say that B. Okay, it's very tempting to say that B is actually this B, but no, this B is not this B. In fact, this B is actually this point here. Alright, this point here. This is your B. Alright, so why is that so? Because any point that is within here and onwards, you do not have any light coming out from the swimming pool. I repeat, any light beam that has angle of incidence more than 49, you will not be able to see it because light cannot refract out of the swimming pool. All it can do is that after the incident angle is greater than 49, all it can do is to have total internal reflection. That's why you cannot see, which is why in this region here, okay, this region here, right, you are unable to see the light because all the light has been totally internally reflected back into the swimming pool instead of out of the swimming pool. Okay, so calculate the distance AB. So to calculate the distance AB, we will use some trigonometry. So this angle here, if I believe your E-math should be quite proficient. So this angle here will be 49 degrees. Use alternate angles, and therefore we are able to find this length here, this pink length here. Okay, it's a bit messy, but okay. So using our trigonometry, you can use tangent. Alright, so let's use tangent. So we say tangent 49 is equals to opposite over adjacent, which is your AB over your 1.2. Okay, so find AB. Tangent 49 times 1.2. AB is equals to 1.38 meters. Okay, 1.38 meters. Alright. Moving on. Okay, so we have a lenses question. So for lenses question, quite straightforward. First of all, no-brainer. Let's always use this light ray to draw. So I will always like to use this as... Okay, I will always like to use this. So this will be what I want to use. So you align the image, the object, and then this origin. So you just draw a line. Okay, nothing too difficult. Now, how about the other light beam? So we will use this. Okay, you can use any of the 3 light rays that you see in your textbook, but I like to draw this. Okay, so let me draw this horizontal until this point, and then from here, what we're going to do is that at this point here, okay, let me highlight this point here, all right, this point here, or in red. Okay, this point here must align to this green dot here. Okay, so you try to align them. Okay, I think something like that. Okay, and then we draw a line. Done. Okay, so now still the solution is not done because, okay, because if you were to draw this, right, you will get it wrong. Over here, I need to draw a dotted line. Okay, all these are dotted lines. Why? Because all these lights are imaginary. Okay, all these lights are imaginary. So this means that all these light here are real light rays. And this dotted line here and here, okay, these are what we call the imaginary light rays. It's what your eyes perceive to be. So if you like, you can draw your eye here lah. Okay, draw eyeball here. Okay, so now, we have already done draw two sets of light ray, incident, refracted, virtual from X to O, and show how I is formed. Okay, we have already done it. Okay, so I show you that the cyan, those in cyan is the virtual rays. Okay, so label the focal length F clearly. Alright, so no need to say this is the point F. Easy. Okay, this is where your focal length. State two characteristics of the virtual image form. Now, more often than not, amongst my own student, they ask me, teacher, do I need to memorize the table in your notes, in your textbook, etc.? And my answer is no. We do not memorize it. And if we don't memorize, how do we know the characteristics of the virtual image? So let me teach you. It's quite simple and it's very intuitive. Look, so here, this part here, okay, this part here is what we call the image, right? And then this line here is your object. So let's think about it. If we compare the height of the object is 2 units, whereas the height of the image is 1, 2, 3, 4, 5 units. What we can say? We can say that the image have been magnified. Why magnified? You see, your object is 2 units big, but you see the image as 5 units big. Obviously, this is magnified. It becomes bigger. Alright, so we will say that the image is magnified. Okay, virtual image. All right. Okay, so the virtual image is magnified. What other thing can we say? Okay, so two characteristics of the virtual image form. So we cannot say that this is a virtual image because they already say that this is virtual image. So we will say that this is the image is also upright. Now again, what it means by upright. So look, you see this image is above the axis. Okay, so this object, okay, this object is above this axis. So let me too many colors, it's a bit confusing. Okay, so let me erase this first. So what I'm trying to say is this object is above the x-axis. Okay, it's on top. So object is on top of x-axis. And likewise, what is my image? Where is my image? My image is also on top of x-axis. Therefore, we say that this is upright. Now, how will inverted be like? Inverted will be something like, let's say I have an object that is upright here, but my image is like this. Then we will say that in this case, the purple and the green is inverted. Okay? But in this case, in this answer, to answer this question, This one is, okay, if you compare the red line and the green line, the image is the red line is on top, the object is also on top, so we say that they are upright, okay, upright and magnified. Okay, question 4. Figure 4.1 shows a reservoir on a hill that is used to supply water to new housing development. The gate holding the water is not open yet. The reservoir is 40 meters above the lowest point of the water pipe. The water volume is estimated to be 1.3 times 10 to the power 7 meter cube. Calculate the mass of the water if the density of water is 1000 kg per meter cube. Okay, pretty easy. Mass is equals to rho times volume, density times volume. So I have my density is, so I have my density is 1000, and then take note, because this is in meter cube and this is also in meter cube, so I can just multiply them. 1.3 times 10 to the power 7. So we get 1.3 times 10 to the power of 1, 2, 3 plus 7, 10. Okay, I trust that this is I won't say basic EMATs, but by now I trust that those who are watching this should be proficiently good at their EMAT, okay, to deal with the shit. Okay, I forget what's this topic called, but whatever. Okay, after the water pipes are constructed, the gates is open and the water rushes into the pipes. The thermal loss due to friction force in the pipes are estimated at 10%. Calculate the velocity when it reaches the bottom of the pipe. Now, in this kind of question, first thing that rings a bell is that you need to recognize that this is an energy question. Okay, now energy question means that we need to use what? We need to use our famous, and this is what we call the laws of conservation of energy, which means, what this means is that you can see that as the water is here, let me use another ink. The water is here. Oh, not good enough. Let me use another one. Okay, the water is here. Alright. Let me change the stroke. Okay, the water is here, and then when the water reaches here, can you see that there is a drop in GPE? And this accounts for why the water is rushing out with velocity, which means that when the water is rushing out with velocity, it means that GPE has been converted to KE. So in this case, we will write GPE is equals to KE, but not quite. Okay, so when we are working with conservation of energy, right, we need to take into account the energy before and after. So before, we only have GPE when the gates are not up. After, we have two things. We have two energy source. Number one, there is KE, because there is velocity, the water is rushing out, there is KE. But another one is that there is a frictional forces estimate to be 10%, which means we need to discount 10%. So we need to plus frictional losses. So how much is this? So how do we calculate this? Okay, so let's, but first of all, we want, what do we want? We want the velocity. So we only want KE. So KE equals to GPE minus frictional losses, and is equals to GPE minus 10% of GPE. Okay, 10%. Okay, 10% of your conversion from GPE to KE, and therefore we can find the we are able to find the GPE. Okay, now, so here comes another problem. We know, okay, I'll write on the side. So we know that KE is half mv squared. Alright. So then GPE, this is KE, this is GPE, is equals to mgh. Now, some student will use the mass here and then plug it in. Well, you can do that, but strictly speaking, it doesn't matter. Alright. Why is that so? It's because if you see here, if let's say we assume that GPE equals to mgh, GPE equals mgh equals to KE and equals to half mv square. So what you notice is that mgh is equals to half mv square. You can cancel out, which means the velocity of the water rushing out is independent of the mass. Independent means it doesn't matter lah. I don't care what is the mass. You can put oil, you can put whatever liquid. The water or the liquid will be rushing out at a certain velocity that is dependent on the height and the gravity. So in this case, I would say it's quite straightforward. Let me rewrite the equation. So half mv square, okay, half mv square is equals to 0.9. Why 0.9? Because you are minusing the 10%, 0.9 mgh. So I cancel the m, so half v square is equals to 0.9 times 10 times your height. What is my height? My height is 80 meters. Okay, and then you can okay, for those who are quite weak in math, so let me do the math for you. So it will be 0.10 80 times 2. Okay, so v square root this whole thing. Alright, so 0.9 times 10 times 80 times 2, and I square root. Okay, so the answer will be 37.9 meters per second. Okay. Alright, so question C. The figure 4.2 shows the complete housing development project. The pump is needed to transport water for storage in the water tank. Calculate the work done by the pump to transport 1 kg of the reservoir water to the tank. Okay, so okay, anyway, so in this case, what you're gonna recognize is that if let's say my water level is here, okay, on top of the reservoir, and it's something like a, it's something like a manometer, right? If you recall your manometer, so it's something like, it kind of like look like a manometer, like that, a very fat one. So this is your reservoir. So this is your reservoir. This is your house. Now your house on top, this is somewhere. This is the house lah. Okay, the house. Okay, so this is okay. So but you need to pump the water all the way to this water tank here, which is another 10 meters. So, well, you already know that the water will, if the water level is here, it will also be here. So what the pump needs to do is to give additional energy just for this 10 meters height of GPE. Therefore, the work done to pump and transport 1 kg of reservoir water to the tank is very simple. Work done is equals to force times distance. And what is my force? Force is 1 kg times 10 times, what is my distance? Another 10. Okay, so why my force is 1 times 10? So because over here this is 1 kg, right? So this is your weight. Your force is your weight of the water. So it's equal to 1 times 10. Alright, so it just happens to be 100 joules. Okay, easy. Okay, moving on, part 3. Explain how would you obtain your answer in C part 1. Okay, so I have basically explained it, but now the hard part is how am I going to write it in words? Okay, how are we going to write it in words? So first of all, what we're going to say is based on conservation of energy, okay, the GPE at the building site will also be the same. Okay, and have a height of 80 meters. Okay, basically what I'm trying to write in words is that essentially here is 80 meters, here is 80 meters. Okay, by the fact of conservation of energy, because you see all the GPE gain here, so all the GPE gain here will be converted into all the KE loss here will be converted into GPE gain back at this point. Alright, hence hence the additional energy by the pump required is only to supply to the water for another 10 meters of height, okay, to overcome gravity. Alright, that explains. Okay, question 5. Figure 5.1 shows an analysis of two forces acting on the forearm bone when it carries an exercise ball. Okay, weight of the ball is 30 newtons. Bicep muscle exert a force FB on the ball to hold the ball at rest. Taking moments about X, calculate FB. Okay, so pretty straightforward. So we have, okay, let me use another ink. We have this, and then let me use. So we have this, and then we have force here, FB, and then this is my pivot. Okay, so in this case, like all moment question, we will say that we will use the principle of conservation of momentum. Okay, principle of moments, not conservation of moments. Principle of moments. Alright, principle of moments. Okay, so what we will say is moment clockwise is equals to moment anti-ACW. Okay, anti-clockwise. So this is my clockwise, this is my anti-clockwise. For those who don't know what is clockwise and what is anti-clockwise, look at the clock. This is 12 o'clock. Okay, the clock turns this way. That's why this is called clockwise. Anything that goes the other way is anti-clockwise. Alright, just a public announcement for, I don't know, maybe someone just don't know why is it called clockwise or anti-clockwise. Alright, so what is my moment clockwise? My moment clockwise will be 0.8, because this is in cm, we will use 0.8 meters times the force, which is 30. Okay, moment clockwise must be equal to moment anti-clockwise. So sorry. So this one is anti-clockwise. Alright. So yeah, so anything that goes this way is anti-clockwise. So moment anti-clockwise is equal to 0.1 times Fp. So you can find Fp is equals to 0.8 times 30 divided by 0.1, 240 Newton. Okay. Alright, there are actually three forces acting on the bone. Calculate the magnitude Fx and state its direction. Okay, so if in this case, we will look at it like it's like a free body diagram. Okay, so you have a bone, not a very nice bone, but whatever. So this bone actually has a weight of the ball here, which is 30 Newton, and then it has a force here pulling up, which is 240 Newtons. So now, why is there another force here? Oh no. Okay. Oh no. Okay, why is there another force here? Now, the reason is because I will tell you what's the answer. The answer is downwards. The reason is because if there is no downward force, okay, this means that what? If I were to remove this means that what is my net force based on this free body diagram? My net force is upwards of 210 Newton. So what does it mean? You doing your bicep curl and then your forearm flies, this whole thing fly upwards. Not possible, right? So that is how our body works. Our elbow, okay, this elbow portion will have to give a force downwards so that your forearm will not fly upwards. Okay, so that we will have no net force. And how much is this force? 210 Newton. Because my downward force is now sum together this and this, 210 plus 30 must be equals to 240. Okay, so well, I already give the answer. So 210 Newton, not upwards, sorry, is downwards. Okay, done. Moving on. Assuming all other conditions remains the same, state and explain the effect of the change in direction of Fp on its magnitude. Okay, now right now we have a force in this manner, Fp. So Fp, what do you guys think Fp will be? Okay, so what will Fp be? So Fp, they never ask for state and explain the change in direction on its magnitude. So they only want to know how will the value of Fp be compared to this 240 that we calculated. So I'll give you the answer. Fp has to be higher. Okay. Why? So because we need to explain. State. So this is 1 mark. This is my state. So we need to explain. So why? So whenever explain means why. Why like that? Why So we need to explain why. So why is that so? Is because as you can see here, alright, right now it is no longer a perpendicular, which means your moment arm has been reduced. So if your moment arm has been reduced, okay, if your moment arm has been reduced, then how can the muscles compensate to lift this exercise ball up? Okay, the only other way is, you see, is that your force B will be greater in order to compensate. So let me use this equation to explain. Okay, not to explain to the examiner, but explain to you guys. Copy. Copy. Paste. Okay. So you see, if let's say because this is not perpendicular, okay, so this cause what? This cause this distance, right? Okay, to decrease. And if this distance decrease, in order for you to have the same moments, right, this one has to increase. Therefore, we say that FB has to be higher. This is because the moment arm length has been decreased when FB is acting in there is not sorry there is that when FB is not acting perpendicularly to the arm. Okay, all right, so that's the reason. So take note, moments, okay, is always force times distance perpendicular. Right, I need to emphasize this. It's not just distance, it is force times distance perpendicular. Okay. Alright. So question 6. At a glance, I know that this question is on pressure and then your rho GH. Okay. So let's see. We have a pump and then we have a kind of like a barometer. There's a height difference, liquid A, liquid B, state the figure. Okay, so the graph in figure 6.2 show how the density of liquid A and B varies with temperature between minus 20 degrees Celsius to 120 degrees Celsius. Refers to 6.1 and state and explain which liquid has a higher density. So we refer to this diagram. So how do we read this? So first of all, we need to understand that here is atmospheric. Now, why do we have this column of height here? Okay, why do we have this? Oh, sorry, no. Okay, why do we have this height column here? Is because the liquid will have to create a hydrostatic pressure so as to balance out with the atmospheric pressure. So in this case, this is what we call the datum. So by means of rho GH, okay, rho GH is equals to atmospheric. So you see, one of them, HB, if HB is shorter, so if this is smaller, this is, okay, so G is the same for both. Okay, it's 10. So how do we balance it? So if H is small, rho have to be high. And conversely, if my H is high, my rho will be low. Or in other words, the density must be low in order to create the same atmospheric pressure. Okay, I hope this is clear. And therefore, based on this diagram, we know that liquid A liquid B, because they want a higher density, liquid B is of a higher density. Okay, state and explain. Okay, so we need to explain why. Because it has a lower, bad English, shorter height. Okay, because it has a shorter height, which means its density is higher to produce the same pressure to work against atmospheric. Okay. Refer to 6.2 and hence explain if the temperature of the setup in 6.1 is more or less than data. Okay, so we need to look at the part where we need to look at part of data. So here, so we have liquid. This is liquid A. This is liquid B. Okay, so based on setup 6.1, we know that, okay, so we already established that at 6.1, the density is higher for, okay, the density rho is higher for liquid B. Okay. Okay, so how do we answer this? Hence, explain if the temperature setup is more or less than. So it needs to be more because after data degree Celsius, liquid B has a higher density as shown. Okay. All right. Question 7. Flyaway hair is hair that spreads and stick out in all directions. 爆炸头 in Chinese they call it. Okay, sometimes I think you guys see in some of your fellow classmates or schoolmates, they come in to school with what in Chinese we call it 爆炸头. Okay, the hair go in all direction. Okay, never comb, not tidy. Anyway, so instinctively most people try to tame flyaway hair with rigorous combing, but this action only worsens the hair condition. So for guys, I think it doesn't really affect us, but this typically affects the female, okay, where they typically use their comb to comb their hair to kind of like straighten it. Okay, so to flame flyaway hair conditioner, which are products that provide smoothing effect to the hair, can be used. So everyone probably should know what is conditioner. Okay, so this product contains cationic polymer. Cationic means what? Cation. Cationic means cations, positive charge. Okay, polymers that are positively charged. They already explained. Polymers that are positively charged. I'm trying to show off. At one end, while the other oily ends remain electrically neutral. When used on wet hairs, these polymers attach themselves to the hair stands and remain in place after washing, giving hair a soft, silky feel. Explain why vigorous combing worsens the flyaway hair. Okay, so what we learn is that, let's say I have hair. Okay, so then I have okay, never mind. Let's use another example. Okay, I think you guys should be more familiar with this. Let's say I have a rod, and then you are very familiar with what? We are very familiar with let's say I have I don't know, cotton wool or cloth lah, whatever. Okay, some cloth. Okay, some cloth. Okay, some cloth. Okay, so what you do is that how they create static is that they rub the rod. Okay, they rub the rod. Sorry. One moment. Okay, never mind. So basically how you can create static is that you have a rod and then you have a cloth. Okay, you can rub it. Okay, rub the rod against the cloth and then you can create static. And how does that happen? It's because when you rub, the friction takes away electrons from either the rod to the cloth, or the cloth transfer the electrons to the rod, vice versa. We won't know. Okay, so likewise, this is also the same. You have your hair, so you have your hair, and then you have your comb. Oh my god, my comb is ugly, but okay, you get my point. Okay, you have your comb. So you comb, so the hair is like your fabric. Okay, your hair is like your fabric, and then your comb is like just another non-conductor. So as you comb your hair, you are basically rubbing the comb against the hair, and this kind of rubbing motion basically transfer the electrons either from the comb to the hair, and or the electrons from the hair transfer to the comb. Okay, we really would know. Okay, this question doesn't really need us to know. All right, so we don't need to know the direction. We just need to know that there is a transfer of electrons in either direction, either from the hair to the comb or the comb to the hair, whatever. Okay, so explain why rigorous combing worsens flyaway hair. It's because as the comb combing creates more friction by rubbing against the hair with the comb. Okay, therefore this transfer electrons from the hair to the comb, or vice versa. Alright, so hence this makes, so what happens is that you mix the hair negatively charged or negatively charged lah, okay? Makes the hair charged, which causes it to stick out. Okay, so basically, the more you comb, the more friction you introduce, the more exchange of electrons from the hair to the comb, and hence you are making your hair more charged. All right, show figure 7.2 shows a polymer attracted to the strand of hair that is charged due to rigorous combing. Okay, draw the charge in the strand of hair and the polymer. Now we know that this is negatively charged because the polymer is one end positive, the other end neutral. Okay, so what we're gonna do is that we will draw a negative, we will draw a positive, and then because they say one side because in this case they say that it's one side negative, the other side will be neutral. Now neutral, how do you draw neutral? We don't draw neutral by drawing nothing. We draw one positive and one negative to indicate it is neutral. Okay, so in this case over here we have negative attracting with the positive. Okay, hence explain how the hair conditioner are able to tame fly away hair. So you can see, right? You can see as as the polymer sticks to the hair, the oil kind of sticks to the hair. This part here, like I said, if you have negative and positive, this whole thing here. Okay, that means if you take a look at the polymer and the hair as a single body or a single entity, the net charge is 0. I repeat, if you take the hair and the polymer as a single body or single entity as one unit, you see them as one. Two come together to become one. You see that they actually form a neutral charge. There is no charge, and if there is no charge, your hair will not be flying out because of static. Okay, so what we're gonna say is that the hair conditioner, or rather the positive charge from the hair conditioner will be attracted to the negative charge hair. Okay, this forms so together, which means this creates together, both will become neutral charge that stops the hair from flying away. Okay. Alright, I hope that you guys notice that I tend to write a bit more whenever I'm asked to explain, as compared, although it's only given 2 lines, but I tend to write a bit more, and that's what you should do. But not write rubbish, write essay. But what this means that, you see, when they say explain, right, we really need to explain the why. Always tell why. Alright? So if you're able to explain the why, that's how you can get the marks. So every time you see the word explain, they are talking about why. Alright? Okay, moving on. Okay, light emitting diode LED needs to maintain a voltage to emit light. The student investigate the minimum voltage using the circuit in figure 8.1. So 8.1, you have a fixed resistor, you have a LED, you have a rheostat. Okay, and then you have your battery, your EMF. Okay, so the student gradually increase the voltage across the LED and record the minimum voltage at which the LED emits light. Different color of the light are emitted from the LED when the voltage across it changes. The results for some different LEDs are as shown. So if you want to get red from the LED, you need a minimum volt of 1.7, blue you get 3.6, or yellow is 2.1, orange is 2.0, green is 3.0. So the rheostat is set at 500 ohms, and the minimum voltage recorded when by the student when the LED just turns green. Calculate the resistance of the LED. Okay, so let me erase all this and then write it this way. So we know that the rheostat has 500 ohm resistance, and we want to calculate the resistance of the LED. Now, so this is a little bit of database question, so we need to study them. So turns green. So we need to know that when the LED turns green is it has a voltage. So we know that the LED has a voltage of 3.0 volts here. Okay, or in other words, the potential difference is 3.0. Now, this shows that this is kind of like a potential divider question, but maybe not so much. So let me discuss what's happening. So whenever we have an EMF, okay, so you have 9 volts. Now, as the charge passes through different resistance, so in this case we have resistance number 1. Let me use another ink. We have resistance number 1, 2, and 3. So every time it passes through a resistance, okay, there will be a potential drop. Okay, so in this case we don't know what is the potential drop, but we know that the potential drop across the LED is 3.1, and then the potential drop across the rheostat we also don't know. So the PD across the rheostat we don't know, the PD across the fixed resistor we don't know. But what we know is that at the end, so if I start off with 9.0, at the end here I must have 0 volts, which means that as the current goes around the circuit, it must drop by 9 volts, which means the PD of the resistor plus the PD of the rheostat, okay, I repeat, the PD of the rheostat plus the PD of the fixed resistor plus the PD of the LED add together must be equals to 9.0. And we already know from here that the green resistance has a minimum volt of 3.0. Therefore, we know that the PD of these two combined has to be 6.0 volts. Okay? Hope my lengthy explanation will help you guys understand. So calculate the resistance of the LED. Now we can approach this using like a potential divider kind of way. So we don't know the resistance, we call it RLED over R total times EMF is equals to 3.0 volts. Okay, so what is my R total? So RLED, what is my R total? R total is also RLED plus 330 plus 500 times 9 equals to 3. So let's just do some math. 9 R LED is equal to 3 RLED plus 830. Okay, so let's do some basic math. So we have 6 RLED is equals to 830. So RLED is equals to 830 divided by 6. 830 divided by 6. 138.3 ohms. Okay, 138.3 ohms and 138 ohms. Okay. Explain what the student can do to change the LED from green to red light. Okay, like I said, how do we change the LED from green to red light? So we want the red light. So in order for it to have red light, you need it to have 1.7 volts across PD across the LED. So what we can do is that since the resistance of LED is fixed, the resistance of the fixed resistor is also fixed. What we can do is we can increase the rheostat. So why is that? So when you increase the rheostat, right? If you understand, I thought for this video I really don't have time to go through or deep dive into how the potential divider works. Okay, but essentially what you need to understand about potential divider is that the resistance with the highest resistance will get the highest share of PD relative to the EMF. Okay, so how do we get 6 here and how do we get 3.0 here is all purely based on proportion of the resistance. I am not too sure whether by saying this any one of you here could understand, but anyway, I don't have the luxury of the time to go through. I hope if there is a demand for it, if there's a lot of people who follows me on my Instagram, drop me a DM and say please have a video to show and explain how this works, then okay, I will do it. Otherwise, as of now I don't think that I will want to do such a thing. Alright, so anyway, so what we can explain what the student can do is that, okay, the student can increase the resistance of the variable resistance. Okay, this will decrease the PD across the LED. Hence, it will reduce PD. Sorry. Not hence it will reduce a bit. Hence it will produce red light. Okay. Okay. Okay, so a potentiometer can be used to vary the voltage across the LED. Draw a new circuit in the space below that includes the following parts: LED, wire, DC supply, and potential meter. Draw an ammeter and voltmeter in the correct position that measures the current and the potential difference across the LED. Okay, what is potential meter? Basically, potential meter is a wire lah. Okay, and let's see how you draw it. So we have a DC circuit. As usual, you have your battery. Okay, I will draw the potential meter, and then what we're gonna do is we will draw the LED. Hold on, let me see the symbol for LED. Okay. Okay, and then and then we have a wire. Okay, so then we have a voltmeter, and then current, like this. Okay, so what this gonna do is that, you see, what it's gonna do is that if I were to put it here, okay, if I were to have this, so this wire, right? So we will say that this is wire, and then this is your potential meter. Now, what is a potential meter? A potential meter basically is just a wire with very high resistance. So the longer the wire, right? Okay, the longer the current passes through the wire, right? The higher the resistance. And therefore, if this wire, right, if I can change where I place the wire. So if I place the wire on the potential meter at the very start, which means I only have this little short distance, right? And then short length means low resistance. Low resistance means over here the voltage will be high. Okay, so if my potential difference across the LED is high, then we can change the color. And then likewise, I can change. I can adjust. I'm able to adjust the. I'm able to adjust the wire and put it further down. And then can you see the length now is very, very long. And when the length is very, very long, then the resistance across the potential meter will be higher, and likewise the PD across your LED will be lower. Okay, so that's how we draw it. Okay, now question 9. So question 9 shows a circuit used to investigate current in parallel circuits when the variable voltage supply is varied. The circuit has an ammeter A and a voltmeter V as shown. Okay, so figure 9.2 shows how the current L and R changes with voltage. So what they are talking here is this and this, how it changes with voltage across. So the variable voltage supply is such that the ammeter is 2 ampere. Okay, this is gonna be something critical as we work along. But first, question A. Explain if lamp A obeys Ohm's law. So we say no. Okay, quite obvious is no. So this is the lamp L. So no, because the gradient is not fixed. or you can say, or the resistance is not constant as the current changes. Okay, so in order for you to have an ohmic conductor, right, you need to have a constant gradient, or in other words, the resistance have to stay the same. So R equals to V over I. So this ratio must stay fixed. Okay, calculate the resistance of the resistance wire if the voltmeter V is 6.5 volts. Okay, so this is a bit tricky. So first of all, we want to find this R. We want to find this R here. Okay, so and then they say specify that this is 6.5 volts. Now, in this question over here, they say the ampere here is 2.0 ampere. So the first question is, how are we supposed to find R? So to find R, we need to find the PD over I. Okay, we need to find the current here. And then we need to find the PD. And we already have the PD. The PD is this. So we have the PD. We need to find I. So how do we find the current? First of all, over here we have one current. We just need to find this current here, I2 here, because the sum of I2 plus 2.0 ampere will be equals to the current that we want to find. Okay, so how do we find? So we will have to make use of the graph here to help us. So from here, okay, we know that at current 2 ampere, the light bulb, this light bulb L, will have a potential difference of 6 volts. And then because we know that both of them are in the same parallel, if the PD across here is 6 volts, hence the PD across here will also be 6 volts. Okay, so likewise, we know that the potential difference across R is also 6 volts. So we trace up, we go across, and we realize that this is 1.25, which means the current at R is equals to 1.25. Therefore, we will say that the current across R is 1.25 ampere. Hence, the current across the wire is equals to 1.25 plus 2.0 equals to 3.25 ampere. Okay, so we basically know that this is 3.25, and hence now this is very easy. We can find the resistance. Resistance is equals to R is equals to V over I. So 6.5 divided by 3.25, you get equals to 2 ohms. Okay, 2 ohms. Right. Okay, so for this question, you really need to pay attention to every single details. If you miss out on these details here, right, you may not be able to solve the question properly, or you may even get stuck as to what to do next. All right. So next, if the resistance wire is replaced by a new wire of similar material and length, but the diameter doubles, calculate the resistance of the new wire. Okay, so resistance is equals to rho L over A. Okay, so now based on the fact of proportionality, so we can say that R1 over R2 is equals to A1 over A1 over 1 over A2. which also means that it's equals to A2 over alright, so I will just write it properly. So okay, so this is the ratio, right? So this part here, this is the ratio. Now this is a bit of a trick question because they say the diameter is double. So most likely what I observe is that tendency is that we will think that the A2 is equals to 2 times of A1, but this is wrong because why? Because area equals to pi r square, or you can put this as pi d square over 4. Now if my diameter doubles, so if my diameters become 2d square over 4, you see what happens. It becomes pi d square. So if you compare pi d square with pi d, right, actually when you double the diameter, the area increased by 4 times because of the square power. And hence, we would say that A2 is not 2A1. A2 is actually 4A1. And therefore, we can say that 4A1 over A1 equals to R1. What is my R1? R1 is 2 ohms over R2. And then when you cancel, you recognize that 4R2 equals to 2 ohm. R2 equals to 0.5 ohm. Okay, 0.5 ohms. Now, it makes sense because if you take a look at this, we say that resistance is proportional to the length, but inversely proportional to the area, which means now when my diameter doubles and my area increase by 4 times, my resistance will actually decrease by 4 times, which is 2 divided by 4, and hence we get 0.5 ampere. Okay, right, I wouldn't say it's just a little bit tricky, but otherwise it's quite straightforward. Okay, question 10. So question 10 is on electromagnetism. So let's take a look at how we can solve this. Draw the magnetic field around the side of AB of the coil due to the current only so that the coil turn clockwise as seen by the eyes. Okay, so well, this is a little bit mouthful. So clockwise means like that, like I said. So which means that you are experiencing a force here and a force here. Okay, so that you see your moment arm cause it to rotate this way. Your moment arm also cause it to rotate clockwise. Alright, so the force on AB is upwards, the force on CD is downwards. Therefore, current due to the current only so that the coil turn clockwise as seen by the eyes. Okay, so in this case, the side of draw the magnetic field around the side of AD of the coil due to current, so that okay, so this is okay. So in order for you to create a force, create a force downwards, right, you first need to recognize that there is a force this way. Okay, so let me draw it this way so you can better see. So when you're looking into B, okay, so this is B. Okay, how about I draw it here? So north, south, this is B. Now we have a magnetic field this way. Let me change another color. We have magnetic field from north to south, north to south, north to south, north to south. Okay, so how can we create a force upwards? as analyzed just now. How do we create a force upwards? Which means to say we need to have a magnetic field that is in this manner. Okay, this is, let me use grid. Okay, we need to have a magnetic field that is in this manner. This will be in this way, this way, this way. Okay, so the magnetic field will be turning in this manner. Why is that so? So let me show you what happens. So when you have the green lines, and then you superimpose with the blue lines, these blue lines are the magnetic field due to the permanent magnet. And then the green lines are the magnetic field due to the current passing through AB. Okay, passing through AB. And what do you notice is that I need you to pay attention here, here, and here. Now, at a cyan zone, right, you will notice, if you can see in the diagram, that both the green magnetic field and the blue magnetic field combine and superimpose together to get it stronger. Okay, and then the pink portion, what you notice is that the magnetic field, the blue magnetic field and the green magnetic field, they oppose each other. And then what we notice is that the net effect is that we have a case such that we have more magnetic field below, but we have a stronger magnetic field at the bottom, but a weaker magnetic field on top, which is as shown in the pink. And therefore it creates, because there's more magnetic field at the bottom than at the top, it creates an upward force. It pushes up. Okay, so yeah, so it's, if you ask me, it's quite hard to get this 1 mark. Okay, I would have given 2 marks instead of 1. It's a bit stingy. Okay, moving on. Okay, moving on. So how draw and label the necessary parts to ensure that coil ABC turns clockwise continuously. Okay, so this question quite straightforward. You can find this on your textbook, but I'm just gonna draw it anyway. So first you need your split ring, commutator, and then you need your little brusher. Okay, you need your copper brusher. Then after that, it's connected to a battery. Okay. Let me see. Yeah, okay, correct direction. Okay, the current have to flow this way, come out this way. Okay, the current have to come out this way, go in this way. Alright, done. Okay, the figure shows a brushless DC motor that can be constructed using string magnets. The magnets in the middle turns clockwise at this instance. Okay, so it's turning clockwise. So state the polarities of the magnet at position X, Y, and Z. So let's have a look here. So here the current will flow this way, go in, come out this way. So using your right hand grip rule, okay, if you use your right hand grip rule, your thumb, okay, I'm trying to draw a thumb. So see, this is upwards, you use your right hand grip rule, okay, and then this is your thumb is pointing this way. So this side is north, this side is south. Okay, so then because this is rotating, clockwise. Okay, so this Z will also be south, so that what it can push and cause it to spin this way. And of course, this will be north, this will be south. And hence, the answer is south, south, and south. Yeah, okay. So explain, so after the magnets rotate half a turn, it remains stationary, and explain what can be changed to allow it to continue rotating clockwise. Now, so what happens is that, imagine now Z is here. So now Z is here instead of no longer here. It rotates and comes here. So Z, remember, this is south. So, south and north, they attract. And then over here, the south become north. And then north and south attracts. So it doesn't rotate anymore. So what can we do here? So there's a few ways we can do. We can do it. We can change this. So why? How can we change this? We can change this. Change the EMF into an AC current. Now, why AC current? Because when you change AC current, it allows the current to go left and right. So which means that all these magnets here will be able to change polarity, allowing this magnet, right, to also change and continue to rotate. Okay, change the EMF into a AC. Change the current from a DC to AC. Okay, so with the change to AC current, it allows for the current to change position. Okay, oh sorry, not change position, change direction. This changes the polarity of the two electric magnet constantly. Keyword is constantly because AC current keep changing its current, so you need to mention about constantly, hence allowing the magnet to continue to rotate clockwise. Okay, finally, section B. So section B, as usual, take note of all the data. Every single piece of data is important. So let's quickly run through. We have a design label, 4 ticks, and then number 3 is the annual energy cost. Number 4 is the annual energy consumption, and then you have your, what's 4? They never say what is 5, 6, 7, 8. Okay, it's okay. So they only care about 1, 2, 3, and 4. So figure 11.2 shows energy label for one brand of TV which has diagonal screen of 32 inches. The annual energy cost is not shown on the label. So part A, label in figure 11.2 shows the annual consumption of the television is 66 kilowatt hour. Assuming there are 365 days in a year, So explain what it meant by annual consumption of 66 kilowatt hours. Okay, annual means that the TV is able to consume 66 kilowatt hours of electrical energy in a year. Okay, assuming what? Because over here that assuming that it is used 5 hours daily. It is used 5 hours daily. Okay. Calculate the on power consumption by the TV when it's produced sound and picture of the television. Okay, so we will have to use this to work backwards. So 66 kilowatt hours to be used for 365 days, and each day is only using 5 hours. Therefore, we have 365 times 5, 1825 hours. So the power, in this case the power is equals to energy divided by total time. And therefore, we have 66 kilowatts over 1825. So you get 0.03616 kilowatts. Okay, which works out to be equals to 36.1 watts. Okay. Okay, calculate the annual energy cost of the television, which will be displayed on the energy label. Okay, so energy cost is equals to energy use per year times price. So in this case, it's 66 kilowatt hours times, what's the price? 27 cents. And therefore, okay, energy cost is $1.782. Okay, $1.782. Alright, that's quite low. Explain why annual energy consumption and annual energy cost is only an estimate. So as it mentions, they assume that you on TV for 5 hours. Okay, so one reason is that it assumes that the TV is only on for 5 hours a day. Now, realistically, sometimes people can on 10 hours, 20 hours, maybe they don't even switch off their TV. So this is an estimate, okay? So it's not real. It's really not real because we wouldn't know. Some people may not even on a TV in a day. So, 5 hours. And therefore, it is only an estimate to represent a general population usage. Alright, so the TV is given a rating of 4 ticks. To be rewarded 4 ticks, the condition is as follows. 0.3 times, okay, you have this equation, and you have this equation. The screen energy is expressed in square decimeter. Calculate the screen area of 32-inch TV and express the area in square decimeter. So, let's see. Over here we have important information which I didn't go through, but I did see it. So the area is, because they want in decimeter square, so the area will be 39.9 times 70.9. So area. Okay, let's see what we get. 39.9 times 70.9. 2828 dm cube. Hold on. I think this is wrong. Okay, first of all, they want it in decimeter, so this is in cm. This is in cm. So 10 cm equals to 1 dm. Therefore, this is actually 3.99 dm times 7.09 dm. So it's equals to 9.99 times 7.09. You get 28.289 dm square, and therefore round it off to 3 sig fig, you get 28.3 dm square. Okay, explain if the rating of 4 ticks is accurate. So let's plug this into here and here. Okay, so we have 28.3. Okay, so let's see what do we get. So 4.3224 times 28.3 plus 20 times 0.3. So this part here is this part here is 42.69. And then likewise we do it on the other side. This part here is 22.77. Okay, so what is the condition? The condition says that if your power is greater than 22.77 but smaller than 42.69, you belong to 4 ticks. So yes, yes, it is accurate as the power is between the condition of 4.269 and 22.77. Okay, the power consumption of a TV is declared as 50 watts if the voltage supply is 240 volts. Explain if a fuse of 10 amp is suitable. So let's see. What's the power. So power 40 watts. So power equals IV. 50 equals to I 240. So I is equals to, let's calculate the current that will pass through this TV. So 50 divided by 240 to ampere. So the answer is no. Okay. So no. Why is that no? It's because the fuse rating is way too high than the rated current going through the TV. Okay, so this will not, or rather the fuse will not protect the TV in the event of short circuit. Okay, basically what I'm trying to say is that you see here the current here is 0.28, 0.208, whereas the fuse is 10. This is way too high. So our standard guideline is that we want it to be higher than this, but not so high. So actually the correct fuse to use is about a 1 ampere fuse. Okay, so basically you can imagine, let's say I have a short circuit and then the current reach like 9 ampere, way higher than what the TV is supposed to experience. So it's already burning, it's already melting, the temperature is very high. Still the fuse will not break because the fuse that we put in at 10 ampere is too high. Okay, so other than the fuse, describe one possible safety feature that the manufacturer of this TV adopts to prevent consumer from okay, so if you take a look at a TV, right, all the TV covers are actually made of plastic. So in this case, we say that it will be double insulated. Now, double insulated means the casing, okay, the casing of the TV is made of plastic. On top of it, the internal circuitry, right, also have another insulation. Basically, it's like if you see the wires of the TV running within the TV, right, it is covered with another layer of rubber. Okay. Okay, question 12. Figure 12.1 shows the construction of a simple loudspeaker. A coil of wire is wrapped around a paper tube attached to the loudspeaker when there is an alternating voltage of 230 volts in the coil. The cone moves left and right with a frequency of 50 Hz. Describe what it means by alternating voltage. Okay, so alternating voltage, it means that the direction of the voltage will be constantly changing. Okay, so maybe you can go here 230 volts and then suddenly it can rotate backwards to 30 volts. Calculate the period of the motion of the cone. So you have a frequency here, so frequency equals to 1 over t. So the period t is equals to 1 over f equals to 1 over 50 equals to 0.02 seconds. 0.02 seconds. Okay, draw the direction of the current in the coil copper if the cone were to move left. Okay, so you want the cone to move left, which means you need a force to the left. So let's use Fleming left-hand rule. So first of all, let's label every single thing. So okay, so what you will notice is that so in this case, right, in order for in order for there to have a force, if you use Fleming left hand rule, you will notice that there must be a current that is, hold on, let me try. Okay, the current must be coming out. Okay, let me zoom in. It must be coming out here. Okay, coming out means come out, come down, go in. Alright, so it must be coming out like this, and then going back in here, into the page. So it's coming out of the page here, and then into the page here. So the direction is downwards, if you were to trace it. So if you were to trace this wire, you come down, you notice that, okay, it coming out of the page and then into the page. So that's why it's downwards. Okay, explain your answer in part C. So how do we explain? So basically you're just going to explain using Fleming left hand rule. So based on Fleming's left hand rule, with the magnetic field pointing downwards and the force pointing left, the current of the wire must be coming out of the page when seen from the top half of the loud speaker. Okay, so essentially what I'm trying to say is that I want them to focus here. This is my top half of the loudspeaker. So if you were to use your Fleming left hand rule, so magnetism is down, the force is this way. So if you try your Fleming left hand rule, I can't show you here, I'm only sharing my screen, but if you try, you will notice that the current, right, will be pointing out of the page. That means if I can show it to you in 3D, okay, so let me use another color. Okay, so this is the green portion, this is this is this. Okay, so if you were to use this is force, this is magnetism, this is your current. Okay, so father mother child. All right, okay, so describe how the sound speaker generate a sound wave. You may draw a clearly labeled diagram if it helps you to answer. Okay, so basically you have a diaphragm here. This is your diaphragm. Okay, so what happens is that the diaphragm, this is your diaphragm, so you have your air particles. Okay, so when they vibrates, right, the diaphragm, this diaphragm will push this air will push this next air, and this air will push this next air, and this way. So then each of them will oscillate by itself, and then we form a compression and refraction. So let's see how I can answer it. So to answer this, the diaphragm of the loud speaker will push the air molecules as it vibrates. Okay. The air molecules next to the diaphragm, next to the speaker, will also collide and heat the next adjacent air particles. This creates a region of high pressure, compression, and low pressure, refraction. Okay, and hence air okay, sorry, let me draw properly. It's not very nice. Okay, so how you should draw is draw something like this. You have your compression first, then you have your refractions, and then you can draw again your compressions, and then your refractions. Okay, so you say this is compression, and then this is refractions. Okay, and hence sound is produced. Okay, so explain how the loudspeaker can produce a louder sound. So what we can do is we can increase the voltage so that the current will increase. This increases the force on the diaphragm, the speaker, and increases the amplitude of the air particles vibration. This increases the loudness of the sound. Okay, so basically what I'm trying to say is that if I were to increase, if instead of 340 volts here, I increase to 400 volts, and therefore the current passing through all your circuits, all the coil here will also increase, which produce a greater force, and then the loudspeaker will vibrate harder, and when it vibrates harder, it creates a larger amplitude that causes the air particles to vibrate more violently, and hence higher amplitude. Therefore, we we always say that the amplitude of the sound wave is proportional to the loudness. Okay. Alright. Last two questions. Either for figure 13.1 shows a forklift lifting a 2000 Newton crate on a wooden pallet. Figure 13.2 shows how the vertical velocity of the crate varies with time, and as it accelerates uniformly for half a second before moving up at a constant velocity. Okay, so this is the graph. 1 second, let me have a drink. Explain what it means by accelerate uniform for 0.5 seconds. So what is acceleration? Acceleration means that the rate of change in velocity. Oh no. Okay, so let's try the rate of change in velocity is the same for the halves seconds. Okay. Calculate the acceleration of the crate. Express your answers in SI unit. So all you need to do is find the gradient. So in this case, quite straightforward. So the gradient is 40 minus 0 over 0 0.5 80 meters second inverse 2. Okay, so 80 meters second inverse 2. Because they want it in SI unit, this is how we express it in SI unit. Calculate the vertical distance traveled by the crate in 5 seconds. So in order to find the vertical distance, we find the area under the graph. So the entire area here. Okay. So to find the area, this will be, this is a trapezium, so half times sum of parallels sides, half times 0.5 plus 1.45 times the height is 40. So you get okay 190 cm. Okay, 190 cm. Okay, I made a mistake here. This should be cm. Okay, because I didn't pay attention to the units here. So this should be cm. Okay, so this is cm second inverse. Alright. Okay, so figure 13.3 represents two of the forces due to the interaction between three bodies, the crate, the pellet, and the earth. The weight of the pellet is considered negligible. Draw and label the reaction force for each of the force drawn in figure 13.3. Okay, so in this case, I'll help you guys. The red one is the red one. Okay, so what this means is that as much as the earth is attracting the crate is also attracting the earth. That's what it means by Newton's third law. Okay, because it's earth on the crate. Okay, it's a force of earth on crate. So this is force by crate on earth. Sounds funny, yeah, yes. The crate is having a gravitational attraction to the earth. Sounds a bit counterintuitive, but I will explain in some other videos. Okay, this is actually quite a long explanation. Draw and label the reaction force for each one, and then okay, so we still need a pellet, so we have a force due to the pellet. So equal and opposite, so like this. Okay, so the blue ones and the red ones. By referencing to answer in part 1, calculate the resultant force on the crate and hence the force exerted by the pellet on the crate during its acceleration. Let's see. Calculation in what? Part 1, resultant force on the crate. Okay, so we will use this as a free body diagram. So this is our free body diagram. We have the weight, and then we have the pellet here. Okay, so calculate the resultant force on and hence the force exerted by the during its acceleration. So first thing first, they say that during its acceleration, when there is acceleration, there is net force. Okay, whenever there is acceleration, so in this case, F net is equals to what? What is my net force? So there is a net force F net here. Alright, so what is my net force? My net force is equals to reaction force minus the weight. And what is my net force? My net force we can calculate using the acceleration. So let's find the resultant force first. F net is equals to, what's the mass of the crate? 2000, which is 200 kg. Okay, so F net equals to F net equals to M A equals to 200 times acceleration. What is my acceleration? My acceleration 80 cm per second, so it's 0.8 because this must be in meters. Okay, so this is 160 Newton, and my force, my weight is 2000 Newton. My F net is 160. This has to be the sum of this. Okay, so 2160 Newton. Calculate the rate of work done by the forklift from 0.5 seconds to 5 seconds. Rate of work done. Rate of work done. Trick. Rate of work done means power. Okay. So rate of work done means power. So how do we calculate the power? Let's see. Okay, we can do this. We can use this formula. I don't know whether if anyone have taught you on this, but you can use this formula. Okay, you can use this formula, power equals to force times velocity. Or not, we can also use power equals to work done over time. Alright, so what is my force? My force is 2000. My velocity, you can see from here, 0.4. Okay, why 0.4? Because 40 cm per second equals to 0.4 meters per second. Alright. So it's 800 watts. Okay, otherwise you can find, you can use work done over time. Basically, what we can do is you find the distance traveled here. Okay, the distance traveled here. So you have work done equals to force times distance divided by the time taken, which is 4.5 seconds. You will also get the same answer. Okay, last question. Or 13 or the design of a refrigerated room is to store perishable food involve calculation of a cooling load. A cooling load is the amount of heat that has to be removed from a room in order to maintain the room at a suitable low temperature. Product load and internal cooling load are examples of cooling load. So part of cooling load is due to the heat that must be removed from product or food to keep them fresh. This type of cooling load is known as product load. The product load is hence the heat that must be removed from the product to maintain its refrigerated temperature. Wow, okay. The following is some of the information needed to calculate. Okay, so basically what they are trying to say is that you have a fridge and then you put your, I don't know, your apple, right? In order for the apple to cool down in temperature, right, you need to take heat out of the apple. So this is what they call the product load. Okay. So the mass of apple 4000 kg, initial temperature of the apples 25 degrees Celsius, temperature of the refrigerated room 5 degrees Celsius, specific heat of apples 3.65 kilojoules per kg degree Celsius. Another cooling load is the amount of heat that must be removed due to the heat generated by the lamp. So again, this fridge also have a lamp. The lamp also gives out heat. So in order for you to cool the fridge, right, you need to take heat out from the lamp, you need to take heat out from the apple. Okay, so product load or number of lamp is equals to lamp times number of hours used per day times number of lamps. 3 lamps in the cold room rated at 100 watt each, running 5 hours a day. Explain what it means by specific heat of apples to be this. Okay, so this is just a basic definition. By now you should be able to answer this with ease. So it means that 3.6 kilojoules of energy is required to raise the apple's temperature, to raise the unit, keyword unit mass. This unit mass means 1 kg. Unit mass of apple's temperature by 1 degree Celsius. Okay. Calculate the product load QP of the apples to keep them refrigerated at 50 degrees Celsius, or 5 degrees Celsius. So how much, and basically is what we want to do is we want to find out how much energy we need to take out from the apples to keep them at 5 degrees Celsius. So QP is equals to MC delta T. So what is my mass of apples? Because they want the product load of apples, and then my specific heat of apples is 3.65, and then delta liter is 25 minus 5. So let's see what we have. Oh, very big number. So the number is 292,000 kilojoules. Okay, 292,000 kilojoules. Okay, should be quite straightforward. Calculate the internal lighting load QL in a day. So in a day, so we'll use this. It's gonna use three lamps in cold room, each at 100 watts, running at 5 hours. So Q is equals to 3 number of lamps times the power times the time. Okay, so it's 3, the power is 100, the time taken is 5 hours, so you need to convert to seconds. Let's see. 5 times 60 times 60 times 100 times 3. Whoa. Okay, this is in joules, so let's divide by 1000. So this is 5,400 kilojoules. Okay, 5,400 kilojoules. Right. Every 24 hours, 2 workers arrive to transport the refrigerated apples to the supermarket, and a new batch of 4,000 kgs of apples is brought in to replace the old batch. Hence, calculate the heat in watt that must be removed from the refrigerated room in a 24 hours day. So, in total, how much energy must be removed from the room? So the room has 2 parts. You have the Q apple, that means the heat removed that we need to remove from the apple, plus the Q from the lamp. Okay, so it will be equals to 292,000 plus 29740 kilojoules. Okay, so now, but we want power, so power equals to energy over time. So we will use the energy 29740 divide by, because they want watts, we need to times 1000, divide by the time, 24 times 3,600 in seconds. Take note, the time here must be in seconds. So three four four two watts. Okay, 3442 3440. Okay. Rate the heat calculated in part B. I is the overestimate of the true cooling load rate. Suggest 2 reasons why this may be so. It's an underestimate. Now, why is that underestimate? Reason number one. Okay, reason number one. Reason number one is that there may be heat loss. Sorry, heat gain heat gain to the room. So that's why it's an underestimate, because we never account for the heat that is traveling. So we have a fridge, right? Heat is also going in from outside. And then the fridge motor will also have to take out this heat that is coming in on top of the two loads, a lamp and then an apple. Next thing, we also need to say that they say suggest means we can say anything. So there are also heat given out by the workers during loading and unloading. So basically, when the worker go into the room, the refrigerated room, they also emit heat, and then the fridge will also have to remove this heat that's given off by the workers. And hence, in that sense, we also underestimate by not accounting for this kind of load. Explain why the cooling air condition vents are placed on top of the room instead of the bottom. Okay, so this basically, we have a room. Why we want to place like a vent here on top is because by now you should know cold air sinks and then hot air rises, so it forms a convection current. Okay, so this is to allow convection current from forming as cold air sinks due to it having a higher density, and hot air will rise. So what? Why we want a convection current? So that the room can be cooled down faster and easier. Okay. Alright. This is really a very long walkthrough. I wasn't expecting this to be so long, and judging from this paper from Zhong Hua, it's both. It is, in my opinion, very tedious. As someone who has done many physics questions, it is also very draining to me, and it's very tedious. Not to mention that I need to explain and stuff like that. So I hope that you guys can appreciate the kind of work that I'm doing, and all I need is that you can share it with your friends and any fellow students that you know of that is taking O levels, and I hope that this walkthrough will be really beneficial to those taking O levels this year, and also any other batch of student that will be watching this in future. Okay, so that's all for today. Bye bye.